Now we're going to tie together the action potentials of the pacemaker cells with the contractile cells and see how they work together to cause coordinated contraction of the heart tissue. So none of this should be too new here. These action potentials should look familiar, but it might be new looking at it this way. So we're going to be looking at this node. This is our SA node, sinoatrial node. And this is where there's autorhythmic cells that determine heart rate. How do they fire? They are autorhythmic and they've got this pacemaker potential caused by funny currents, funny channels that allow for spontaneous depolarization over and over and over again. So they're going to depolarize and then send that signal to adjacent contractile cells that are branched as well, right? So that branching is an efficient way to spread a signal quickly. And they're connected by intercalated discs that contain gap junctions. So when you have these autorhythmic cells fire, it's going to cause firing action potentials all the way down the entire heart tissue, even down here. This isn't showing that far down, but it's going to spread. These action potentials also look familiar. Here's that plateau, that delay that's due to calcium channels opening. So the reasoning behind this is that we want to have all the heart muscle contract at one time. It's like having a stalled car. One person can't push that car and move it. You have a whole group of people that all push at the same time and allows that car to move. That's like the blood. If one of these little cells can't pump blood anywhere, it's not going to do anything. But if the entire heart muscle contracts at one time, primarily we're talking about the ventricles is where the most force has to be generated to force the blood out into circulation. And imagine that your blood has to travel through the entire systemic circulation from that one single contraction of your heart. It's got to be pretty strong, and it is. All right, so this depolarization that we're seeing here, these electrical currents are coupled to that contraction, right? This is just looking at the electrical activity here, the action potentials, but then that is going to be always coupled to contraction because this is muscle tissue. The SA node is setting the rhythm, but there is a second node that can set the rhythm if the SA node is damaged. So you'll see that in this image here. This is looking at the same idea, but in more detail. So we've got step one, SA node is going to spontaneously fire action potentials. That's right here. And those action potentials are going to spread across the atrial muscle, the myocardium of the atria, and depolarize the atria. These are called internodal pathways to get to the AV node. So that's what's happening right here. This purple shading represents depolarization spreading across the atria until it gets to the AV node. So if this is 3, this is number 3. This is the AV node. So that's a second group of pacemaker cells that don't actually set the pace unless the SA node is damaged. So if the SA node is damaged, this node will kick in. It has a lower rate of firing. So this is one thing that occurs, cause of bradycardia, which is a low heart rate. If you have bradycardia, it could be due to damage of the SA node. There's other things you'll see with that as well in the electrocardiogram. We'll come back to that. The important part of the AV node right now is that there is actually a delay here because we're kind of converging all onto this one node that causes a delay. That's important because coupled to this excitation is contraction. This delay allows the atria to contract before the ventricles. So while the atria is contracting, this signal continues down, but it has not reached the ventricles yet. So atria contract before the ventricles because of this delay. We've got, continuing this pathway down, there's this AV bundle that's in between the atria and ventricles right here, and then the bundle branches. So this is, make sure I have this right, this is let's just go right here. This is for, here's for traveling down these bundle branches that are in the intraventricular septum. Remember that term? The divider between the two ventricles. That's where the action potential travels, and then it comes back up this way. Back up this way is the Purkinje fibers. So that's what's happening here. So why this is happening is, first of all, you can see all this purple, it all happens at once because it's rapidly going across all the ventricle tissue at once. However, it is going bottom up. So depolarization is initiated down at the base, the apex of the heart, and travels up this way. That allows for contraction to be slightly sooner at that apex. That's pretty convenient if we want to force blood up this way. We don't want to squeeze the toothpaste tube at the top of the tube. You want to squeeze it at the bottom of the tube, or your family will get annoyed at you. So same idea with the heart. It's going to squeeze bottom up, and then it's coordinated. It's almost all at the same time.